this is a symposium on maps, cognition, and representation, and it's really following up on a lot of the themes of Nora's talk, particularly on the variation, both individual variation and environmental variation in the use of cognitive maps. And it's organized with Roberto Casati. I myself am Pablo Fernandez Velasco, and the other symposium is Mi-Sung Kim. And we will be tackling the connection of cognitive maps and mental representation. You know, the question is, does the mind form map-like representations? And in particularly, we will be looking at what are the contexts, what are the situations in which the mind seems to be forming this type of representation. First, environmental variation, and this is something that Nora touched on when she made the distinction between open environments and dense environments, and then individual variation. So first, Mi-Sung will be discussing cognitive maps for a 3D world. And a lot of the research that's out there, a lot of the research with mice, a lot of the research with humans, is really thinking on one level of the environment. And it's really a focus on 2D environments. But a lot of the environments that humans nowadays navigate are like this, right? Where it is a 3D environment, and if I have a map of the environment, where is the point? Is it really on top of the one on the bottom floor? Is it on the same place? How do we integrate the frameworks of things as they happen on a 3D world, in which humans can move vertically as well as horizontally? And then she will go further to other types of environments, like how do people navigate on non-flat surfaces that are embedded in 3D environments, like a sphere, like the one you have here. And what is going on? Do humans rely on, do people rely on dimension-reduced maps or volumetric maps, humans and other animals? Then Roberto Casati will take it from there and also look at variation in the use of cognitive maps in different environments, and look at what he calls non-cooperative environments. He takes cognitive maps to be an inference to the best explanation, but this inference is predicated on cooperative environments, environments where, you know, this approach works. And there are some environments that are navigationally non-cooperative, in the sense that they make it near impossible to automatically generate a cognitive map of their layout. And then I will close the symposium by discussing variation from person to person, but specifically from culture to culture. So I will look at how different cultures across the world do navigation, in particular expertise in navigation. So I will touch a bit on London taxi drivers, which are the famous example from neuroscience. And then I will go quite far away to the middle of Siberia to look at what Evenki reindeer herders and hunters are doing. And does expert navigation depend on the use of cognitive maps? And when you look at Evenki reindeer herders, it seems that something quite different is going on, even though these people are very, very good at finding their way. So that will be it. Because I'm talking later, I wanted to do a quite short presentation. And what we will do is, you know, we'll get up, rather than wait at the table. We'll get up, give a talk, one short clarificatory question if you have any clarificatory questions, then the next person, then we will all sit at the table, have an open Q&A, invite Nora as well to join us for the Q&A, and also try to, you know, bounce from each other. So if there is a question that any of the other symposiums has something to contribute to, we'll try to have a kind of conversation going. Thank you so much. I'll pass it on to Mi-Sung.
Hello, I'm Mi-Sung Kim. Thanks all the organizers for making this conference and the symposium. So following Nora's excellent keynote talk on cognitive map and spatial representation, I'm going to talk about diverse shapes of cognitive map for a three-dimensional world, such as open space where we can fly or float, or curved surface like a skateboard park, or a little planet where a little prince might live. Yeah. So there has been extensive research on neural mechanism of mapping two-dimensional space, and we know that place cells in the hippocampus respond to particular two-dimensional location in the environment, and head direction cells signals which direction we are facing, like a northeast. And how do we navigate and build a mental model for three-dimensional space is relatively understudied. And one obvious question is 3D spatial mapping a simple generalization of 2D system, such as place cell previously responding to X and Y coordinate, will have a spherical receptive field centered at X, Y, Z, and the head direction cells that responds to both latitude and longitude. And in such cases, there will be symmetry in our mental model. So we are equally good at remembering vertical and horizontal location. However, this might not be the case because of the shape of the environment and the constraint on the gravity. So in a multi-level building like we are sitting now, like the first floor, second floor, third floor, people are often more confused of knowing whether we are on a room 101 versus room 201 compared to whether we are on a room 101 or room 102 on the same floor, because we mostly navigate within the same plane. And even on a volumetric space, if we have to remember the location of a floating object, then we sometimes see asymmetric precision of recalled memory, like the stretch along the vertical axis, meaning that less information. In contrast, vertical information might be better encoded in some sense because of the gravity. When the gravity polarizes the environment with up and down, so we naturally know whether we are facing up or down compared to whether we are facing a west or east. Therefore, in one of my previous fMRI studies, I showed that when people are floating or flying in a volumetric space, some part of the brain, like the retrosplenic cortex, have a higher information for the vertical dimension compared to horizontal. And some brain care more about the horizontal axis. So these findings suggest that the nature of 3D map is highly dependent on the shape or the type of the environment as well as behavior task. And dimensionality is another important feature of cognitive map. So most mammals, including humans, live on a surface. So this 2D surface embedded within a three-dimensional world. So we can use either a full three-dimensional map or a flattened map. So each has pros and cons. So the full three-dimensional map is more flexible and it will allow planning beyond the navigable surface. Whereas 2D map is a more efficient and compressed encoding of space. So I wonder which type of the map people use on this kind of surface, and whether these two maps interfere when people have to retrieve the spatial memory or distance in such environment. So to answer this question, I built a virtual environment similar to skateboard park, which has flat and a curved surface, and I placed 8 objects on this surface. So on the concave part, the distance between some location like A and B, has a shortcut. In terms of the 3D Euclidean distance indicated with the blue straight line. and the path distance on the surface, the red line is longer, whereas in the flat part, either path distance on the surface or 3D Euclidean distance, is identical. And people, move around on this surface as if driving a car, and their viewpoint was always parallel to the surface, like this. So that means that two-dimensional map was sufficient to navigate this surface and encode the location relative to the surface. However, we found that the participants still retrieve three-dimensional map automatically, because after learning and testing their location on this surface, we gave a test to judge the distance between objects from their memory. So if they only care about the surface map, then the distance estimate for the AB and the AG should be identical, but we found a small but significant underestimation bias for the path distance on the curve, which implies that the interference between 3D and two-dimensional map. So it's neither purely 2D nor 3D. It's some kind of like a mixed map that we use. So now let's ask and how we build such cognitive map. So there are two types of information allowing us to know where we are and build a map. So the first, we can rely on external spatial cues, such as trees or bus stop or church. Like as soon as I see the tree, that I know that I'm in front of the trees. However, if the environment is dark or foggy, then we cannot see immediately of this such landmark. We can still know where we are by integrating the integrating path or the self-motion information. So for example, I came from the bus stop and walked 100 meters east, then I can guess that I should be around the tree. So both spatial cues and path integration are complementary and important mechanism for navigation. But today I'm going to focus on the path integration system because it's one of the basis for cognitive map formation, and not just humans, but all the animals can have a good path integration capacity. So so the computational mechanism for path integration is like one of the most well-studied and favorite topic in the spatial cognition research. And basically, a neural network where like place unit, like with each this color dot, if they are connected cleverly with the velocity unit signal, like the north movement direction, east or west movement direction. So this velocity unit has a spatial connectivity to the place unit. Then they can shift the neural activity to accomplish path integration. And we know that in the brain, there is neurons encoding for direction as well as speed. But one caveat is most of the head-direction cells found on the previously, they mostly care about where animal is facing on the surface, and they are insensitive to the orientation of the surface. So in this example, if the mice is moving around on the floor, and then if it climbs up the wall, so it's like a 90-degree rotated surface, but the head-direction cells mainly care about whether animal is facing like 45-degree on both the vertical and horizontal wall. So that predict that if only two-dimensional, the surface direction and the velocity is integrated, then path integration will become inaccurate on a non-flat surface because of the difference in geometry. So let me give you an example. So imagine that we are starting, we start here on a flat surface, and then we walk like 2 meters straight. and then we turn 90 degree, and then we walk 2 meters again. And if I'm asked to come back to where I started, my intuition will say that I have to turn like 45 degrees to make this equilateral triangle. But if we do the same task on a very small like planet, imagine that I started from the North Pole and then I walk straight all the way to the equator, and then I turn 90 degrees and walk the same distance. Then I'm still on the equator line, and to come back to where I started, I have to turn 90 degrees, not 45 degrees, because of the different geometry. So so that will predict some very specific bias on a path integration system if we only care about the surface direction or the path integration system's constraint. On the other hand, if three-dimensional velocity is integrated, then path integration can be perfect, and then we can also create a volumetric map. So to answer this question, I designed a virtual reality environment. So people wear like VR goggles, and then they are walking on this kind of treadmill. Yeah, and it's a 2-day experiment. They start with the sphere condition, and then do the plane condition, or the vice versa. Yeah, so first, after getting used to the VR system, participant will freely explore this spherical or planar environment by walking at their own pace. So I will show you a video. So now participant is walking on this spherical surface. The left side is what participant would see, and the right side is just the third eye, the bird eye view that participant will never see. So they are passing this yellow chick and zebra or turtle. So it's like a space zoo with a 12 landmark placed at a triangular layout. And on the plane condition, they again have the 12 landmarks on a triangular layout. It's a different type of animals. Yeah, but the rest of the environment looks very similar because I applied the same texture, like this moon-like texture, and the same starry sky, and I also matched the visibility by adding some fog, because on a plane condition, you can usually see it far in distance, but on a sphere condition, that your view is obstructed because of the surface. So I also matched the similarity. And after spending some time, try to remember all these location. Then we'll test participants' knowledge on the space. So there will be a queue, they have to find the dogs, and then first they will look around to see where they are. So now I'm between a zebra and penguin. Then from my memory, I would first decide which direction the dog should be, and then I will walk until until the place where I think the dog is. And then I will get a feedback. So all the animals will appear again. So I will know whether I went to the correct or wrong location. And here comes the path integration task, which we call triangle task. So in the triangle task, that you walk straight on the first leg of the triangle, and then they will turn, and then they will go to the end of the second corridor, and then everything will disappear, and then you have to turn to where you think you started, and then just walk straight until the start position. And here, we only give general feedbacks. So the participant cannot correct their strategy during the task. So let's. Uh, Okay, let's see the result. So I will show, real, trajectory the participant, took, which is a black line, and the red lines on the sphere shows the outbound trajectory. So that is two corridor. So if participants have a perfect path integral system for the sphere, then they have to come back to the start location with this blue line completing the triangle on a spherical surface. However, if they rely on 2D like a Euclidean path integral system, then I expect people to walk along the green line. So the green line is the is consistent with the planar geometry. And as you can probably see with the naked eye, the black lines are mostly clustered around the green lines, which means that participants rely on a path integration system based on Euclidean planar map rather than volumetric map. And here are some quantification of the model fitting for the plane versus sphere, and for both turning angles and the travel distance is much better explained by the plane rather than sphere. And I asked participants whether they had a prior knowledge of the geometry difference between the plane and the sphere. So roughly half of the participants reported that they already know that there are some differences between the triangle on the plane and sphere, and half of them had no idea. However, there was no differences between these two group of people. So which indicate that the explicit, geometric knowledge, is not sufficient to overcome this planar bias. So in follow-up ongoing experiment, I ask whether the landmarks and the imagined layout might help the path integration system. So just to give you some idea, so the path integration system, will inevitably accumulate the error as we move further. So in the simplest case of the linear path integration, let's say that I started from this narrow long room, and then I have to close my eyes and walk until the bed. And while I'm walking, so my uncertainty of the position will go up as I move further. However, if I touch the table on the way, then it will reduce my uncertainty because I know the relative location of table compared to bed. So resetting the errors. And the idea is, even when I don't touch the table, but just the memories of table or imagined table, could induce this kind of effect, reducing the uncertainty. And I think this is also a navigation technique used by expert navigator, which Pablo will discuss may explain a little bit in his talk. So in this experiment, that I give the similar triangle completion task, but at the start of their triangle task, now participants could look around to see the animal to know where they are. While they are walking, so it helped them to imagine the landmark during the path integration task, and the control condition was the animal was always present, so that you don't need much path integration system. Yeah. So let's see the result. So in the baseline learning condition, when path integration is not so necessary, so most participants accurately came back to where they started. So this black line is corresponding to the start location. However, in the test phase, that the landmark was only visible at the start, we again see the similar the overturn bias and that fits with the planar geometry. So it suggests that the imaginable landmark is still not enough to overcome this strong Euclidean bias. However, we did see some benefit of this imagined landmark at the response variability. Yes. So this path integration triangle task research shows this strong bias of path integration system. Then how that will affect our path planning ability? So in these studies, people also have all these animals, and then they have to go straight to dog or penguin. And critically, half of the trial, the path was relatively short, and the half of the trial, people have to plan a long distance to go. And here I show one example. For all the participants. So when they have to start from here and the target is there, when the target is relatively close, most people get really close to the target on both sphere and the plane condition. And the initial angular error, so the deviation from the ideal line, so red line, and this blue path, is quite small, 10 degrees on a plane and 20 degrees on the sphere. But when the target is far away, then especially on a sphere, the people took a route that deviate a lot from the ideal path. So the initial directional error, it becomes much larger on a sphere condition compared to plane. So in the plane, the angular deviation was not so different for the short and the long path. So at the start, it looks like people are really bad at planning their path. However, if we look at the final position error, in a long path, it's larger than the short path. But the difference between the short and the long, on the plane and the sphere condition is not so much different. So there is no interaction effect. And this is because of the curvature. So on a plane, so the position error always scale with the distance and the turning and the error. However, on a spherical surface, we can arrive at the same location via multiple route because it will converge on the surface. So what does that tell? So in terms of navigating on a spherical surface, we could use a volumetric map, and then we can encode location direction, either polar or Cartesian coordinate. And then for the path planning, we just make some 3D shortcut and project it on a vector to find the optimal route. In such cases, it doesn't matter so much whether the target is close or far. However, that 3D map might be too complicated, and if we use instead multiple patches of planar map, so that we have one map consists of 3 landmarks, and this other one, and then it's connected roughly. Then, if we stitch together this Euclidean map, we can still plan the path by approximating it, and and this cartography is also used for our Earth, because the Earth is spherical almost, and then we usually project it on a paper. So I think developing a full 3-dimensional map can be costly and also time-consuming. Therefore, combining local planar map can be a good alternative. And I also did some simulation of path planning based on multiple arranged map, and then I showed that the final position error will be reasonably small even when you use the planar map. And also from ecological point of view, animals will actively interact with environment, and they will correct their mental model of the world rather than relying on a static map. And as introduced by Nora earlier, So there are many studies use impossible like a maze in like Bavarian's group. So they place like a wormhole on a maze so that these two this third part is combined or this like hectagon on that is like distorted. And when people are placed in such impossible maze, people quickly adapt to the virtual environment, then they can find the optimal route, even though it's not consistent with the Euclidean geometry. And people often do not even notice that there's something wrong with this environment. Yeah, so I do think that humans or animal will dynamically like correct the error even when we use an like approximation. Yeah, so to summarize my talk, I suggest that humans can build a mental model of three-dimensional world, and the key neural structure, like the place cells and the direction cells, are involved in representing both 2D and three-dimensional space, but it might be some different precision or asymmetry depending on the shape of the map. And the dimensionality of the map is also quite flexible, so it's not purely 2D nor purely 3D. Yeah, and I think humans do have a strong Euclidean planar bias when they navigate on a surface, so that causes some like systematic error in a path integration on a sphere. However, that does not prevent us to plan a path like reasonably well, because the planar map allow us to find a map find a path by combining. And so probably this is a cost-efficient way of how the brain deals with the complex world. And we talk about all this physical space, but some people like to make an analogy between physical navigation and abstract like conceptual space. That the concepts can be also described in a multiple like axis, like a physical space. And we can speculate that in a multi-dimensional like space, probably dividing and projecting and approximating into a low-dimensional space is a good way to solve the problem. Yeah, so thank you all. Yeah.
Any clarificatory questions? One? Okay.
Hi, thanks for the talk. So I was wondering how far you think that it's like trainable to avoid those biases. So I was really curious, for example, if maybe people who grew up or live in a very mountain-like area, which is of course not spherical, but at least three-dimensional, might have an easier time avoiding those biases or doing a better orientation in a three-dimensional world.
Hello? Oh, yes. Yeah, so that's a very good question. So I do think the environmental, the experience will affect our cognitive map. And I don't have any data, and we don't know anyone who raised in a spherical case. But there are some interesting study from rodents. So there are like mice or rats raised in like a hemisphere inside of the hemisphere. And then they will bring the animal to the flat surface to record their like place cell and grid cell. And on the first day, their like place cell or grid cell like looks a bit odd compared to animal raised in a typical like flat environment. However, like from like the second day onward, they shows like mostly normal spatial firing pattern. Yeah, so it seems like there are we do need a little bit of experience, but this Euclidean or the planar bias seems, has some biological like wiring. And there are also other studies looking at this like neural connectivity of the grid cell. So I briefly introduced about this neural network model for path integration. And this model predict specific type of pattern. So it's like a toroidal pattern for a grid cell. And these studies show that even before animals start like crawling and moving, like at day of like 16th day, the neural recording already shows this kind of pattern, which implies that this 2D path integration optimal system has some biological constraint in these animals.
Here, I'll pass it to Roberto. Thank you so much, Mason. Thank you.
So good morning. Thank you very much for having the possibility of being here. So I'll talk about this notion of non-cooperative environments in a while. First of all, I would like to spend a few minutes, which is maybe interesting given the time budget that I'm being allocated. Let me just start the chroma. On a discussion on a very specific non-cooperative environment, which is the high seas, and about a discussion of the techniques which are used by certain communities that navigate through the high seas for solving a very specific problem, which is not wayfinding, but is land finding. We are talking about Micronesian communities. I never did any field work there, but I read a lot of the literature, primary and secondary, about that, and I present some kind of synopsis of that literature. And I think we also have to be very grateful to some of the great navigators of the Micronesian area for having been the great intellectuals of the 20th century that made possible a transmission of a heritage which went lost because some techniques of navigation that we use as Westerners, using maps and the compass, now GPS, made totally redundant the techniques that were used in those communities. In particular, the figure of Mau Piai Lug, who should be written in great capital letters on all faculties of navigation studies. So let me say something about this situation that you see here. This is a summary of maybe 20 years of studies on Micronesian navigation. There is a big problem. The problem is you have to go to the bottom left hexagonal island or atoll to the top left atoll. So the two green spots, you have the starting point and the end point of the navigation. And the point is, this is maybe more than 20 miles or 200 miles, it could be 800 miles, and you don't see anything. I mean, you're out at sea and there is nothing to be seen. And these are small, low-rise islands, so you can only see them when you hit them. Basically, you see the top of the trees at some point, if there are trees on them. How do you do? And apparently there was a big feat because the first Western navigator, like Cook was not a second class navigator. I mean, he was totally flabbergasted by the fact that these people on small outriggers were able to cross these long distances and have trades, basically communicate and marry across long distances. How could they do? And there are many techniques which have been uncovered by this heritage transmission. There are beautiful documentaries you might want to see. This is a kind of a summary of what we know. So I start from the end point. You have to hit on an island which is very small and totally invisible once you're out on the high sea. First thing to do, enlarge the island. Make it bigger in your imagination. Make it 10 times bigger. So the green spot on the top left is actually larger now, is a big oval. And so when you're there, you have all the techniques that you have on the panel on the top right. When you're close to that, hoping you get close to that enlarged island, then you can rely on some local cues. These local cues are maybe birds that at night go back to the island after having hunted, fish around, fish, the different type of fish that you can see. You can actually see fish because close to the islands there is more fish. Clouds signal islands, and some clouds are actually whiter because they get some reflection from the atoll light, the water. And smell, water color. Of course, there are some contingencies here. Maybe you arrive by night, so you do not see the birds. So maybe you miss, and then you feel you've missed, you have to go back, and it's complicated. But how to get to that enlarged island in the first place? Because this is the point. I mean, you do have some knowledge. This knowledge is part of a long training. The training is maybe 10 years. And it's interesting because it's non-written, it's totally oral culture. So you have to train people orally, doing exercises and a number of other communication techniques. So in this training, you have some knowledge, some historical knowledge of the direction in which you can find that island as well as other islands. And so you start by that direction, which is the black line at the bottom of the sea. But of course, there are environmental constraints, and we're talking about a long navigation, maybe 200 miles. So what happens in this particular case? You are at the trade wind latitudes, which means you have constant winds blowing all year long with some inversion, but typically we blow east to west, 20 knots, steady. And so you have to compensate for the drift which is created by the winds. So you start with another direction. Basically, you compensate and you head a bit to the right of your direction, which is the dotted line. The resultant of this change of direction, this compensation, is that you end up on something, hopefully, which is close to the red line here. So this is the result of your keeping a heading which is off relative to the direction of the island. It's already very complicated to start from the island and keep a direction whatsoever, because you have to, how do you keep a direction? And there are many techniques here again. A typical technique is it is a technique that you find also in other cultures, is the regularity of the wave pattern, which is produced by the trade winds. So the regularity of the waves are typically perpendicular to the wind. And so if you start with a certain direction that you can keep relative to the waves, you can maintain that direction. It's the same thing that you have with sastruges in northern countries, which are patterns of snow in the wind, relative to the wind. Now, and this is one thing to do, but the other thing to do is to keep track of your progress, which is also very difficult because you're just going and going and going, but how much did you go? And when are you expecting to see some traces of the island? So here the literature becomes very murky and complicated to understand, and I have a proposal. I don't think it's, maybe it's not the final story about that, but there has been a lot of discussion about some kind of quasi-magical intuitive abilities to keep track of your progress by using imaginary islands. These are called ATAK, A-T-A-K, ATAK islands, which are imagined growing under the horizon to keep track of your progress. What happens here? So let me tell the story. How is it told by even people by Ed Hutchins, who studied the ATAK navigation. You have a pattern of stars rising. So here, stars rising in the east, and you're trying to move south, that is to the right of your image. As you move south, suppose there is a real island. As you move south, you will see that island move to the left relative to the stars. Hour after hour or day after day, if it is far away, and you can see it. So this is a way for you to keep track of your progress, because you see that you're moving south, because night after night, when the stars rise, you can see the island, for a parallax effect, move to your left. So This is what you do all the time when you walk in the street. I mean, you just see near obstacles moving to your left if you look left, to your right if you look right. And now the story is that, well, you don't have those islands, but you have imaginary islands. And I give you 1 minute, which is a lot in my budget of time, to think of how could it be possible to use an imaginary island to keep track of your progress. I mean, which kind of reliability you can have from an imagination of a fiction of your imagination. Of course, if it really materialized virtually, maybe projected by some kind of app on your horizon like Stellarium, fine, but you don't have anything of that. You have to use that in order to monitor your progress. How could it be done? You already went 34 seconds. So. Back and forth. How can you use an imaginary island to monitor your progress? In the vast open ocean. So the solution to this problem is that you can't. It is simply impossible. You cannot use an imaginary island to monitor your progress. So these islands are there for a different reason. You get some information about your progress from independent computations. And then you mark a star with an imaginary island. So you know that you moved a certain number of miles or whatever south, because you get this information from other sources, which I'm not discussing here. At that point, you create an imaginary island that you use to mark a star, because if you mark this star, the day after, maybe if you have sufficient information to tell yourself that you moved a sufficient number of miles south, another star should be marked by the imaginary island. So this is a proposal, an hypothesis for discussion. But anyway, this is a non-cooperative environment, and you need a lot of redundant techniques in order to cope with such an environment. And basically, I do not know if this goes in the direction of the mental graph theory, maybe, but definitely is something that I would consider to be modeled on a Sudoku constraint satisfaction model. So in a Sudoku, you have a certain column with figures in that, which constrains the solution to that column, and the result further constrains the solution to a certain row, and so on and so forth. So basically, it's a reasoning cascade which is put into place and which is exploited by the navigator. And there is one more thing that I would like to say about the navigators. They spend a lot of time just watching the sea for signs, for changes. One thing that I didn't say is that when you come close to an island and you are leeward to the island, you can get some interference patterns from the waves. The trade wind waves are very regular, but they get choppy when they meet an island. So if you are on choppy waves, that means that you're probably leeward of an island, and so on and so forth. So you put in all these constraints together. Okay, so cognitive maps now, the philosophical part. Cognitive maps are theoretical posits. And we had a presentation by Nora Newcomb before. She was very much presenting this idea. They are theoretical posits. And I think they do get their support, if they get support, from an inference to the best explanation. In particular, their postulation straightforwardly explains certain abilities, such as the capacity to envision detours and shortcuts through unperceived, unvisited places that are connected to places one has visited, one perceives, or one is at. So this is the main idea. You can plan a detour, you can plan a shortcut through a place that you cannot see now, or that you haven't visited. The map is there to produce this ability to plan that detour. And as you can plan detours, and as you can plan shortcuts. You have to explain this ability, and cognitive maps seems to be there to explain that ability. The main idea is that exploration of an environment automatically, in a kind of a system one mode, produces representations of the environment that can be piecemeal, scattered, but are nevertheless organized in a map-like fashion, or in a format that is compatible with a type of retrieval of information for navigational purposes that mimics the type of retrieval that we perform on external maps. For instance, if on a real map, on a paper map, one sees that the present location A is serially aligned with both an unsurmountable obstacle B and the target C, so there is an alignment between A, B, and C, but B is an unsurmountable obstacle. You cannot go through B. One can plan a detour around B. And this is the important point. The explanatory point is that the detour is already present in the map. It's part of the map syntax, it's there. The map is so made that the detour is present in it. And this is why, if you postulate a mental map, you have an explanation of why you can plan a detour, because the detour is part of the syntax. Now, the inference to best explanation, most of it, I would say, and then the effectiveness of cognitive maps, seems to be predicated on what I propose to call, I rehearse some ideas calling it environment cooperation. Some environments are navigationally non-cooperative in the sense that they make it near impossible or non-effective to automatically generate a cognitive map of their layout. Let me say, for the terminology, I use map for a physical map and mental map for a mental map. So when I talk about maps, I'm talking about physical maps. And let me say another philosophical point. I think the characterization of a mental map, given what they're supposed to do, can only be as good as the characterization of maps. So you can use mental maps, but then if you think that they're really maps, you have to characterize maps. If the notion of mental maps is somehow parasitic on the notion of maps, for instance, if both maps and mental maps are species of the same genus, map star, and as we do have clear access to the properties of maps, we see them, we build them, we successfully use them, we revise them, then it is a fair claim that one's characterization of mental maps can be only as good as one characterization of maps. This is actually what I try to provide in a book, which I allow myself to advertise because it is open access, so I don't get any royalties out of it. So in the book, I try to specify what maps are from the syntactical and semantical viewpoint. It turns out to be a surprisingly difficult task to exactly characterize what maps are. We have a lot of intuitive ideas about them, but when you try to make it precise, you end up in some kind of trivial notion or contemptuous notion. So I took the contemptuous way, and well, you can judge by yourself. The notion of a non-cooperative environment, I think I would like basically today just make a plea for a better philosophical, a deeper philosophical work on the notion of a non-cooperative environment. So this is kind of a starting point for a discussion. I take it to be a syntactic notion. Certain features of the environment, the way it is structurally organized, make it a non-cooperative or cooperative environment for navigational purposes. So this is a cooperative environment. Is a drawing of a Sonoran desert. It's cooperative because, given what we know consider the environment, not the picture, consider the environment itself. Based on what we know about the orientation capabilities of humans, we need distant landmarks to be visually or perceptually accessible. And this is what this type of environment provides. So you can monitor your direction, because if you want to go in a certain direction, just take a mountain as a reference point, and you can monitor your progress, because there are many visual landmarks along the way that allow you to monitor your progress. So it's a cooperative environment. This is a non-cooperative environment. And I have a little potential discussion with Nora Newcombs here on this point. This is a totally repetitive environment. Where are you? Well, I'm on a black cell. Okay, tell me what you see from your black cell. Oh, I see a black cells on the diagonal and white cells. Well, where are you? And it's non-cooperative. Peter Strawson had a beautiful discussion of this in his book on individuals. And I think grid-like cities tend to lean on the non-cooperative part. They are not, because we spend a lot of time making them cooperative, but you get lost easily in this type of cities. And they build in a lot of redundancy to help you, but they tend to be very repetitive. And of course, the open seas, in which you don't have any type of distant visual landmarks to begin with. You just see waves. Actually, what happens on the open seas, if you're a good sailor, you have to inhibit the tendency to use whichever visual cues you have, like clouds. You have to inhibit that, because otherwise you get lost following a cloud. I mean, you can follow a cloud for a little while, but then you have to revise. Distinction. I think there is a distinction between non-cooperative or cooperative and non-familiar. You can have a familiar environment. For me, this is, I think, Amsterdam Avenue. I live there, so it's a very familiar environment. Still, it remains non-cooperative. And familiarity, another distinction, could be token familiarity or type familiarity. So when you can become familiar with this type of environments if you live in New York City. And then you can export your familiarity from Amsterdam Avenue to the Fifth Avenue. It still feels familiar. It feels like New York. It's the same atmosphere. But still, it remains non-cooperative. So there is this triple distinction that I would like to stress here. If an environment is non-cooperative, we might do things to it. We might punish it and make it cooperative. So I think this is a notion of environment punishment that we do all the time. We inflict certain punishment to the environment to make it redundant and hospitable to our orientation capabilities. So we put landmarks in it, like beacons, lighthouses, cairns, street numbers, various type of Ariadne's threads. Or, if you don't want to augment it, you can even constrain it. You can constrain it like tracing a path or a road in it, so that you do not even have to resort to orientation capabilities or mental mapping or whatever. You just follow the road. So this is a famous quotation from John Holland. Quote, "Now let me tell how I get to San Jose. I pick the right road, Interstate 880, south, stay on it, and get off at the end. Can we say that the road knows the way to San Jose, or perhaps that the road and I collaborate?" I don't think this is as crazy as it might first sound. Okay, I think it's just half crazy, basically. The road and I collaborate, but the road doesn't know anything. There is a clear fallacy here from the fact that you can reduce the cognitive load by augmenting a non-cooperative environment, that is by paving a road to San Jose. It does not follow that the implement that does the augmentation, that is the road, is performing any cognitive work. The road is not doing anything cognitive. I think if the image is very seductive, it will take quite a lot of arguing to show that it does perform a cognitive work. In a more sober way, we can say that paving roads is a way to reduce a 2D navigation problem to a 1D problem. You just have to follow the road. And here is an environment which is made cooperative, it has been punished by because it was not non-cooperative. What about the open seas? Well, you cannot augment the open seas, you cannot punish them. Maybe you can exploit currents and tides and things like that, and winds, but there is no way to constrain the open seas, and this is a huge problem. So we found a solution. As humans in the last 50 years, we created a satellite position, a GPS. But satellite GPS is basically, and I think it's a philosophical, metaphysical important point, is a creation of a new environment, is an electromagnetic environment, which is created by the modulation of different signals produced by the satellites. And the GPS navigator only sees that environment. It's not seeing you, it's not seeing mountains, it's not seeing lakes. It's seeing only this electromagnetic modulated field. So we could not punish the sea. We created a different environment to go about it. Now, this is a GPS, and we'll say something about that in a second. Non-cooperative environments, be they familiar or non-familiar and unconstrained, pose an obvious challenge to extended cognition theories. We cannot offload our orientational abilities to them because there is nothing to be offloaded to the open seas. We might have the illusion of offloading distant clouds and so on and so forth, but they are illusions. And here is where we might invoke mental maps. But a non-cooperative environment is actually non-mappable or cannot be mapped very well. So there's a kind of dilemma here for people like us. So we cannot use an extended cognition theory here, and it doesn't look as if a mental map theory is going to work. It's kind of a theoretical dilemma, which I may leave for discussion. Now, I want to finish on a very small sequence. I said that the IBE, the inference to the best explanation, seems to be the straightforward way to introduce mental maps. But I said, well, mental maps do not seem to work in certain environments, like non-cooperative environments. It doesn't seem to be feasible to postulate mental maps for navigating the open seas the way I was describing them. Maybe there is a different reason. I'm exploring different reasons for the introduction of mental maps in the psychological world, which is what I call the cartographic bias. So there is a very well-known cartographic bias, not in psychology, in geography, I would say. Most geographers would subscribe to it. They would say that cartographies make us think of the environment in a certain way we would have not thought of hadn't it been for the cartographies. So boundaries, for instance. We think that the real are boundaries, like state boundaries, but they do not really exist. But for the cartography. I mean, you need the cartography in order to project cartographic features into the environment. Even the coastline is most geographers think the coastlines do not exist. And I think they're right. But maybe there is also a psychological theoretical bias. So maps are extremely effective ways to organize spatial information because of their format, or the syntax. Because their format allows us for the at-a-glance retrieval of facts to ground both situated and non-situated spatial inferences. And in the particular case of detours of shortcuts, their map, physical map representation, is physically already present and available, as I said. So Ed Hutchins would have said it is pre-computed. Although I do not see a particular advantage in using the metaphor of computing. Maps do not compute anything. The way multiplication tables don't. What maps and multiplication tables do is presenting the result of some computation or observation. Now, in the case of maps, however, not all contents of map regions are a result of a computation. Some are just there because maps are spatial items unfolding in space. And this is the the reason of this picture. So I switched on my navigator, GPS-based navigator, but I didn't have any data connection. You can try this, and this is what you get, typically. You get a blue dot, which is perfectly true, in the sense it tells you where you are, but cannot be used, because you don't get the map. I see a lot of cognitive smiles on your faces, and I think it never happens to you, it only happens to me. Okay, main claim here, you don't see the map is there. And we can spend a lot of time arguing about that. Every time there is a certain area, a certain syntactic area, which is assigned to a certain environment, even if you are not able to see the features of the environment, the map is already mapping that environment. Here specifically is mapping the place around my home. So places in this gray area already have a meaning, although you are unable to retrieve that meaning, but the meaning is there. The denotation of these places, the denotation of places on the map is already there. And this is a power feature of maps. This is why maps work. Basically, when you do geography, you're not assigning location on the map to location on the territory. You are discovering what are the features of the territory which correspond to a certain location of the map. It's like when you're scratching your lottery ticket, and which you don't do. You shouldn't, it's irrational to do it. You scratch your lottery ticket because you lose, and then you see something behind it, but something is already there. So the geographer is basically scratching this surface to show what the denotation of each of these places is already there. And this is the power of maps. This is what allows the immediate retrieval or shortcuts and detours on maps. And this, I summarize, is why we are looking for a vehicle, the mental map, that mimics the operation we perform on the content map. So conclusions. The inference of best explanation may not be a sufficiently strong case for postulating mental maps, because non-cooperative environments are implausibly difficult targets for mental map representation. And second point, there are at least some reason to suspect that mental maps are theoretical ghosts produced by our well-grounded fascination with physical maps. Thank you for your attention.
Great, thank you so much, first of all, to Misun, to Roberto, and to Nora for all of the interesting talks. It's been a lot of fun putting together the symposium and then listening to all of it coming to life. So I'm going to close things off by looking at, Nora's called it individual variation, but more specifically in my case, I want to look at cross-cultural variation, how different cultures approach navigation and what's the role of cognitive maps in expert navigation. I was very happy to see Roberto actually closing off by discussing cartography, which I've not planned, but I wanted to bring out this quote that incidentally Roberto has, this little short story that Roberto has discussed in a different paper for a completely different point. But that I think is quite interesting in the discussion of cognitive maps in anthropology and geography and a lot of the humanities. They focus a lot on cartography and the cartographic impulse. So the reason I bring it is first because it connects to literature, and second because it's a very nice short story. So if you don't like the talk, at least you'll get Borges. So this is what Borges says in On Exactitude in Science. In that empire, the art of cartography attained such perfection that the map of a single province occupied the entirety of a city, and the map of the empire the entirety of a province. In time, those unconscionable maps no longer satisfied, and the cartographer's guild struck a map of the empire whose size was that of the empire and which coincided point for point with it, right? And you can think that, this cartographer pursuit of the perfect map in Borges' short stories, hyperbolic, but betrays a common fixation with representing the environment around us with as much accuracy as possible, a sense of safety, control, power that we might get from that. And there is really widespread animosity in much of phenomenology, geography, towards what they call the totalizing cartographic impulse. That's exemplified here by Borges' stories, but that they think is behind a lot of the theories of cognitive maps. So this is Ed Casey on place. He writes a lot about place. He's kind of the phenomenology of place person. And what he says is that journeys across the land are integrated into a region. That's mostly how we interact with space and place, right? An ever-growing, ever-changing network of nodes and paths. Here you might think it's closer to the cognitive graphs than the cognitive maps that Nora was discussing before. Regions, however, are not located onto an independent spatial framework, but just in relation to each other. And here Ed contrasts this relational organization of places as experience with the bird's eye view of cartography, right? He says, what we do is really not like maps, right? And Tim Ingold from anthropology really takes on this idea of a region and takes it much further, right? He actually uses it very specifically to argue against the cognitive maps idea as it appears in psychology and neuroscience, but also as well as in anthropology. It's not like all the anthropologists are on the let's hate on cognitive maps camp. And what Tim Ingold says is that just like cartography, the theory of cognitive maps flattens our experience of place into an impersonal space that we look at from above. And instead, what Ingold thinks is that we find the way it works is that it depends on remember routes, not remember locations in a cognitive map. And specifically, it's a kind of ecological psychology take, a kind of Gibsonian idea of we have vistas and transitions. So they're not like a snapshot, but really like the sense of moving through a place. And then when we need to retrieve it, we just get the sense of, oh, we're going through the same tunnel type thing. And this is what we reproduce when we walk. And what he says is the world of our experience is a world suspended in movement. That's continually coming into being as we, through our own movement, contribute to its formation. In the cartographic world, by contrast, all is still and silent. And I think it's interesting for me coming into this literature because my go-to idea of what expert navigation is very good cognitive maps, right? My idea was these people who, probably a lot of you know, London cabbies train for a very long time to develop the knowledge of London. They need to pass a grueling test where they have to be able to call all the streets in between any 2 points. And as a result, their hippocampus changes, right? It's one of the few volumetric changes that you see related to ability, if not the only one, right? And basically, in a nutshell, the posterior to anterior ratio of the hippocampus changes. Kind of part of it grows, right? And what Eleanor Maguire discovered is that ingenious, and the ways he took it is that because it's the hippocampus, that as we've seen is the, hippocampus is the cognitive map, that's the kind of idea. The results suggest that the mental map of the city is stored in the posterior hippocampus, right? So I think if you're a psychologist or a neuroscientist and you think of super navigators, you think something like this. Some very, very good cognitive map. That's what's going on. And what they do, there's some kind of ethnographic work on what they do by Eva Grisbauer. Eva Maria was going to the London schools and seeing exactly what they do. They train with maps, right? Very often they also train with what they call the book. And they do things like cottoning the start and the end location. They then put like 25 and 50% marks. And this eventually, after a lot of training, and this is some work we have also with Eva and with some other colleagues, impossible to find the pointer. What they're able to do after all this crazy amount of training is things like this. You give a London cabbie 2 points in London, and they can tell you all the streets in the trajectory that connects those 2 points. So here the starting point is the orange one, and the yellow point that will appear is the destination, and we ask them how you go from one to the other, And this is what generally they're able to tell us, right? So that's where they
Burley
have to go,
Street,
right?
left Tavistock Street, right Southampton Street, left Henrietta Street, right into Bedford Street, Ford Garrick Street, Ford Cranbourne Street, right to Charing Cross Road. From Charing Cross Road, I would then go left into Shaftesbury Avenue, go to the right to Wardour Street, left into Knoll Street, forward into Great Marlborough Street, sit down on the right.
Yeah, so you can imagine with all of the streets in London, the possible combinations of streets between any 2 points is, it takes all of the rice and the chessboard like out the window. It's like really, really massive computational challenge, kind of combinatorial explosion of what's going there. And that's roughly what we explore in that paper. But here I just wanted to show you how cool it is that they can do this. And of course, not the neuroscience versus anthropology debate, in which they think, oh, how we're flattening out all the experience and the niceness of wayfinding with our cognitive maps. There is also, Nora mentioned Steve Levinson, right? And Steve Levinson is a big proponent of cognitive maps and, very renowned anthropologist. And the reason why he thinks the cognitive maps are going on in a lot of the cases are exchanges like this. He asks Roger where to get fish, and Roger says, they have plenty of fish fillet in the store. I've never seen it. Where? On this side, in the frozen food container, far end this side. So if you're an English speaker, you imagine that this gesture means you go through the shop, the fish is to my right. But what this means is, this is a store that's 45 kilometers away, right? Is that the gesture was to the northeast, right? So you are expected to know that the fish is on the northeast corner of the store. And obviously this is a Guguji Mitira speaker that Levinson is talking to. And that's how they make all of the spatial reference points. They use absolute coordinates. And what's very interesting is that when you have such a system of absolute coordinate, you tend to have also very precise gestures all the time. And you constantly have to know where you're facing with respect to these coordinates. And Levinson says that this requires a cognitive map. And the level of precision is astounding. So he took these people out into the bush, often to unfamiliar locations, and then asked them to point to faraway locations. And their error is like 12 degrees, like 3%. Sometimes for places they've been there rarely, sometimes things that are up to 100 kilometers. And this is, a comparison with Dutch participants who go mushroom picking. So these are people who are out in the forest on the right, in the Netherlands, and people who are out in the bush on the left. Very, very different. And there is this debate in anthropology between the mental map theory people and the practical mastery people, which are like the Tim Ingold people, right? And I think it's a useful debate for a lot of the questions in this symposium. The idea for the mental map theory is that wayfinding is carried out in the light of stored spatial information in the form of a mental map of the terrain, plus presumably some inferential schemes of converting this information into suitable practical decisions and actions. I think apart from this, you also need to update the map. It's something that I think Gail is missing here. But you get the gist from previous discussions. In contrast, for Tim Ingold and a lot of other people, this I think could be the mainstream view in anthropology. Wayfinding is a skill performance in which the traveler, whose powers of perception and action have been fine-tuned through previous experience, feels his way towards his goal, continually adjusting his movements in response to an ongoing perceptual mentoring of his surroundings. This is close to cognitive graphs, but again, it's not so much about the representation of points in a graph as about this transition between vistas. But you could have this idea of, roughly with cognitive graphs, something very similar. And I think it's a bit of the debate is not really necessary in the sense that once you look at the literature of different cultures, what becomes quite clear is that humans use both cognitive maps and route knowledge during navigation. And what varies both across cultures and across individuals within that culture is the degree to which one type dominates the other. And they are in fact complementary, like people do tend to generate this type of knowledge as one. And the idea is you could have route knowledge, which is something like, turn left at the hotel, then turn right at the library, then left at the restaurant, and it's kind of sequential, right? You have like a sequential knowledge, or you could have a cognitive graph. And what there seems to be is a kind of clustering of absolute people versus relative people. There are some cultures in which really seems to be cognitive maps are the main thing that expert navigation involves, and some places where that's really not the case, and it tends to correspond to the kind of spatial descriptions that they use, where the people who tend to use cognitive maps use absolute spatial descriptions. Everybody can sketch a map, so the difference is that if you ask an absolute person to sketch a map, they'll sketch it according to cardinal directions. If you ask a relative person, they'll sketch it according to like where they were looking at the time, or maybe according to the river or something like that. And this is something that a lot of indigenous communities are aware of. They don't see it as a kind of Western versus indigenous contrast. This is Andrew Golovnev discussing this issue of mental maps versus root knowledge. And he says this is what a Nenet person told him. Well, Nenets keep track of their path as if watching themselves from the sky, like a moving dot on a map. On the contrary, Wayfaring Khanty, that's the neighboring tribe in Siberia, recognize a tree and follow in that direction. Then notice a hill and go toward that point. Then they remember every hammock of their hunting ground. Right? If you do this kind of thing, you really need to be very good at recognizing places and stuff. And this is something I'm very interested in, so I've been kind of trying to collect. It's very hard to look at anthropology literatures and just pop up in Google Scholar the way neuroscience or psychology does. So I've been trying to, together with Hugo Spears, collect different data on how people navigate across the world. And here you can see a map, and each of these corresponds to if you go to the paper, each of these corresponds to a reference, right, where you can read more about navigational approaches across the world. But it's really interesting for me, what does expert navigation without cognitive map looks like? Because it might seem like it's an impoverished thing where people need to follow routes. And that seems kind of counterintuitive in some of the environments that people need to navigate. Ingold himself has done extensive fieldwork with Sami reindeer herders in Lapland. He also mentions the Wilbury people, who conceive of the environment as a network of paths. And, there's the Ongis people of Little Andaman Island, who also place themselves in the environment only through movement, like the environment seems to come to being only through movement. They don't consider it kind of like in a projection way. And here I want to zoom into some of my own fieldwork in Siberia with Venki reindeer herders, and also some of the existing work with this community, right? And so if you're not familiar, Evenki are a Tungusic people spread over Northern Asia, and this is very spread. This is kind of all across Russia almost. And they are very famous, even within indigenous communities in Siberia, for being really good at wayfinding. And they are quite clearly relative people, as in, you can see this in how they orient maps. It's like according to rivers rather than cardinal direction. You can see it in their spatial descriptions, and you can see it in their own explanations about wayfinding, right, if you ask them what they're doing. And I think it's interesting because it can, looking at how people can expertly navigate an environment without a strong dependency on a cognitive map can tell us a lot of what's going on. And I don't think it's just cognitive graphs. I think there's much more going on than cognitive graphs that seem to be a kind of lesser version, like you then pay for the premium for cognitive maps and just get unlabeled cognitive graphs. I think there's a lot of different elements going on, very similar to what the constraint satisfaction story that Roberto was talking about. This really took me a while because, again, I was coming with this preconceived idea of, they just have a super cognitive map like London Cabbies. I'll just hang around until we become friends, and then they'll tell me about their cognitive maps. And I asked them, so how do you do it? Just look around, follow your way, go this way, go that way. Just need to know it, just need to grow up in the environment. There's nothing to it. For a long time. And there was this hunter who spent a long time in the taiga, and we would play chess together every day. We kind of became friends for a while on the shore of Lake Chirinda in the far Arctic in Krasnoyarsk Krai. And at some point I asked him, but you've never used maps? Everybody asks, it's no, maps are useless, GPS is useless here. And it's well, I actually use maps because I had to do military training, and then they force us to use maps. And yeah, I actually kind of like it. It's fun. You you have the points, they give you a compass, they drop you somewhere, and you have to figure out by triangulating what spot on this map you are. I was like, right, so is it a bit similar like that to how you like then find your way in the taiga? And just like started cracking up. He's like, are you crazy? Like, has nothing to do with maps. It's just like absolutely no connection what we're doing with anything that had to do with maps. It's just like a game, right? And this is very consistent, going back all of the ethnographic literature even to early Soviet period. Here's Oleg Yakovlev saying, a reindeer herder saying, everything is written in the natural environment. You just need to observe all around you. Brandy Saukas, after spending a long time with a brigade of reindeer herders, says, dwelling on the taiga is based on a skillful attunement to a place while moving through it. So it's this idea of a skillful walking. It's really attunement to place, but that sounds almost mystical. What does this attunement to place come down to? And how does it work for like finding your way and then finding your way back? And I think it comes down to 4 elements in this case, right? One is a particular gait, a particular posture, form of embodiment. Then there's a network of paths, and that's quite close to the cognitive graph story. And then there's hydrological knowledge, maybe also as a form of graph. And finally, a landscape typology, which is doing a lot of the heavy lifting. And if you walk with an Evenki person, they're really hard to catch up with. Even if you're much taller, it's just really like hard. They walk very, very lightly. They seem to be like clambering, and they wear very light soles. They always want to feel the ground as they walk, even though it's super cold. They'll still insist on quite light soles. And this is what Donatas Brandisauskas says. I try to imitate, and he's complaining about how he can never catch up either. The guy is like stopping for cigarette breaks, he still cannot catch up, right? I tried to imitate Alexei's way of walking, notice that he walked differently in different areas. He never took big steps, but mostly walking fast, short steps. He gave the impression of being bow-legged and was simply made for this way of walking. And here's a video by Safona Van Santa of Irgici, a hunter and shaman that they live with, walking through the taiga, and they mention that it's almost like a panther with his pole. He's like leaning on the pole, changing hands with the pole, and constantly sensing all of the environment with several points of contact. And also something he does is cracking branches as he goes, like making different marks on the terrain. And it's very important because it's a way of making, this will be quite clear in non-cooperative environments, because it's, as what Nora was saying, a very dense environment, right? And here you have this kind of environmental adaptation, which is really marking the environment every time you go. And here's where the paths come in. And when I say paths, it's like I couldn't see them, right? They are like really like tracks in the taiga. They are created and maintained mostly through the movement of the herders and hunters, and used to be much broader in pre-Soviet times, obviously with colonization and then the loss of cultural knowledge and the loss of mobility, the network is impoverished. And they have a particularly intricate system of symbols, what they call a ilken in Evenki, right? So the way you make a cut into a tree, the way you like put a log that's fallen and you make it send something, you can convey a lot of things. So you can convey type of landscape a trail leads to, or whether it's good terrain for hunting or for setting camp, or even leaf messages like we have left camp now, back next spring. And finally, there's this system of rivers, right? You ask them to draw a map, first they draw the rivers. You ask them to tell a story, they'll tell you about the rivers. You look at their cosmology, the rivers are what's connecting all of the worlds, the underworld to our world. And they have hydrological knowledge of really vast areas, much vaster areas than they will ever have to explore. And this knowledge is more like a family tree, really is like a network. It's not like Euclidean in a way, I think. And as children, first thing they need to learn is rivers, the way we have like the ABC songs. They have songs of how all the rivers connect together. And you go to a new environment, first thing you go to the river and you make sure you recognize that river, you recognize the tributary. So if you suddenly bump into it, you're like, oh, this is the Muksa. And also how this is useful later, right? And finally, there's a landscape typology. So a lot of it has to do with particular names. So it's toponymy also is a knowledge of landscape names, both of individual names, but also of types of landscape, right? So, and they're very specific names. And once you know the name, you start to recognize that type of landscape. And they carry a lot of information about possible uses, like for where a wild reindeer that you might want to hunt is likely to be licking this type of moss. So, go there if you want to hunt wild reindeer. Or ili means a piece of rock sticking out of a mountain. And they use this also for navigation, because this is what Gabishev, who is a reindeer herder and researcher, says. Thanks to the Evenki knowledge system of the landscape, I can guess the locations of rocks, rivers, passes, and so on, even if I do not know the specific place. So I go there, I'm like, oh, this is this type of place, so likely a river is there, right? And just to see how it all connects together and to show you that it's not really just remembering routes or even remembering vistas or transitions in the way that Gibsonian psychology will have. And this is a map where you have the Tungursa River. You can see that it's not clear by the fact that I just draw the line. And then the Umuksa River on the bottom, and then two tributaries of the Umuksa River. And the Chum is the tent. They always set up tent by the water. And the dotted line there is the prey's trajectory, right? This is a thing that eventually the hunter will hunt, right? And this is what happens. The hunter leaves the tent, and it's like, oh, a prey passed here, right? And you'll think, well, if the prey passed here, then it went perpendicular to me. Maybe I just go perpendicular or go around in some way. But no, they go to the river, right? Instead of going to where the prey is going or doing like a short loop, they really go down to the river, almost like have visual contact with the river, and then they start crisscrossing until they pass the trajectory of the prey, and still they notice that the prey trajectory was there, but they keep going, right? They keep going slightly towards the Tungursa River. You can see that it's slowly deviating, and then what do? They do this. They go to the river and then back, almost as if you were doing like tapping the river and then coming back, and then they follow it all the way to a tributary. Around the tributary, they loop back, find the prey, kill the prey, and then to find their way back, you could think, oh, they just do path integration, right? They'll follow roughly the prey's trajectory back to the tomb. That's what you'll expect with a cognitive map. No, what they do is they follow the tributary down, they find the river, and they follow the river back to their tomb. And it's all egocentric, and the way this is working is they're using the rivers a lot. They're using the rivers as routes, right? You are able to go back to the tomb because you know how the rivers connect, and you're able to recognize the rivers. But they're also using the rivers as boundaries, right? Otherwise, what's the point of going to the Tungursa River? They just want to make sure, like, I am in this area, and within this area, I can wander quite freely. And because I know all of these landscape types, I know where the rivers are. I don't know exactly, as in a cognitive map, but I know, oh, this type of landscape means the river is roughly there, right? Means this is the way to the river. And the way they do is complete immediate immersion in the environment. So let me wrap up. How does it all work together? The gate network of paths, hydraulical knowledge, and toponymical system is something like this, right? Again, it's not just cognitive graphs, it's a lot of systems working together and making constraints that are mutually satisfied in the way Robert was hinting at. And if we want to look at skillful walking, that's how the Evenki will refer to it, versus cognitive mapping. By the way, if you were expecting that there was like some data that, you know, with error bars, or if you were expecting some argument, because this is psychology or philosophy, that's not it. There is like some stories, and now here are some reflections on these stories. And these are some of these reflections I hope are interesting for discussion then with the rest of the symposiums. Is that what's going on in the case of skillful walking will be familiar to a lot of people who've looked at all the discussions of embodied cognition in the 90s and the early 2000s, right? And there is, you know, you might think of ecological rationality, right? A mind can be better off with an adaptive toolbox of bias, specialized heuristics, rather than very computationally heavy, representationally heavy models of the environment, right? You have a bunch of different tools, that biases, almost rules of thumbs, what they call fast and frugal heuristics, and they're adapted to a particular environment. And then you don't need a kind of complex planning of routes and complex planning of complex representing of the environment in an independent framework. And this is a kind of representation light embodied cognition that's going on. And using Safiro's term, it's a dynamic dance in which body, perception, and world guide each other's step. And you can see that in the gait. You can see that in how their perception is attuned to different types of landscape, and this is very much modulated by language, modulated by culture, and the particular environment, right? This very dense environment, you take them to any other place, it doesn't work. And also something that's might be easy to me is because you're like, oh, it's all on the moment, on the go, on the hook. There is a rich cognitive ecology going on here, right? This is at Hutchins, who came up already in the previous talk. The idea of cultural practices, doing a lot of the work in cognition, right? Cultural practice shape active sensing and ways of seeing the world by highlighting what to attend to and what to see when so attending. And this is exactly what we see here. We have this very intricate system of names that completely drives attention and a kind of pattern recognition that then drives all of the fast and frugal heuristics. So they're able to be very representation light only because there's a long period of enculturation, of learning all of these rhymes of how the rivers are, of learning all of these place names, and also of marking the environment, right? So you really see this distributed cognition at work where it's kind of diachronically distributed. They are able to find their way there and back because a lot has happened developmentally and also in terms of environmental transformation. So I would like to thank all of the people in these communities first, all of the expedition team that really, were figuring most of the things out and a lot of the thinking behind all of this. Also some of the collaborators on the work with London Cavis that I mentioned briefly and some funders. Thank you so much.
So there is a kind of representation of rivers. Is there also a representation of watersheds, of separation
like
between river basins?
Yeah, I don't know because I'll have to check. There is a paper on exactly this. I just cannot remember what they say. But yeah, it's an important. I could imagine because the way they use the rivers very often is for areas. Like this is the area in between these two rivers. So they are probably using the sense of the watersheds. It'll be interesting to see. There is a paper by Emma Montova on how they understand rivers and how they represent rivers that came out recently. So I have to look precisely at this question. Yeah.
How much of the trajectory of the hunter is to do with wayfinding, and how much is just evading detection by the prey?
Yeah, that's a good question. Well, I think you can see that in the cases where they don't end up hunting anything, and they do something very similar. They still will kind of keep check on rivers and stuff like that. But yeah, part of the reason, and I wish I had tons of GPS data, but no, that's not the case. I thought I was gonna be going back there a lot and doing more and more techie, psyche things, and then obviously I cannot go back there anymore with all the work going on. So I just communicate with my collaborators there via Zoom. But yeah, you can see that obviously another reason to go around is that otherwise the prey sees you, right? But even then, there is much more optimal ways to go around that don't involve this kind of wandering, even in that example, right?
Hi, Pablo. Thanks, very cool talk. I had a clarificatory question. How do you see this work? Do you think of it as kind of a different, a distinct type of wayfinding that's robust and might pop up in other cultures? So do you see it as a form of skillful walking with some more abstract elements, such as it's just an intermediate thing, but there's a way to fit it within the current conceptual system or something else?
Yeah, I think some of the elements will pop up in different cultures. A lot of the recognition of landscape types, not so much the rivers. I don't think the rivers are going to be as important in some other cultures, but the ways of walking, yes. The things that look like cognitive graphs, yes. The landscape names, yes. But it's something. that it will really need to be researched from the ground up. Like somebody will need to go to these different cultures and check, because the literature is very sparse. Yeah. Should we maybe have everybody from the symposiums and Nora joining at the big table? And yes, I can see that it's exactly the right time for that. Thank you so much.